going to be demonstrating how to best utilize the master background subtraction step that's offered by the JWST calibration pipeline for NearSpec MOS data. So just to give you a little bit of an idea about what the notebook covers, you'll go through the basic introduction, importing, setting up your directories and downloading the data. We'll then first go into inspect the background spectra before we do any kind of background subtraction to any of our science. And this is because I just want to check for any obvious large variations in the background before doing anything. We'll then go ahead and do the master background subtraction and see what default spectrum is returned by the pipeline. And finally, we'll go ahead and make our own master background spectrum and supply it to the pipeline and kind of discuss some options for handling hot or bad pixel contaminants that can sometimes show up in the data and why it's important to actually take care of those problematic pixels. So I'll just give a little bit of intro. So with JWST observations, you're detecting background emission from various sources, including, the Zodiac Cloud, the Milky Way. You got thermal self-emission from the observatory itself, and you also have to account for stray light that is from out-of-field sky. And so to remove this excess signal from your spectral traces of your science targets, the pipeline provides actually 2 standard background subtraction methods, but today we're just going to be focusing on this master background subtraction. And so just to give you a little bit more about what master background subtraction actually is, it's a method that uses a flux calibrated 1D master background spectrum. You can provide that directly to the pipeline, or you can go ahead and have the pipeline generate it using background data from that same observation. And with MOS observations, that background data is collected from those designated background slits that you defined when you were creating the program. And so what the pipeline will do is it'll essentially extract and combine all that background data into a single 1D background spectrum. And that's what we're calling the master background spectrum. And after that point, the 1D background spectrum is then interpolated back into 2D space of the slits so that it can be subtracted from the science data. And I provided here like a really detailed list as well as like the link where you can actually go in and read a bit more about it. But for now, that's all I'll go into that. And I'll just note here that master background subtraction is a viable option for doing background subtraction whenever you have like a large enough area that's source-free background that you can actually estimate a background spectrum from. And you may also find this advantageous when you're, say, observing extended sources. Okay, so let's just jump right in. So here is we're just going to do our general imports. I'll just make note here that we're using the latest version of the pipeline, 1.14.0. We'll also just set up a parent directory here to store all of our results from this run. I'll also just make note here that I have this run flag parameter, which you can set to either true or false. I have it set to false right now because I have already run this data and I just want to simply pull the results that I have already processed. But if this is the first time running the notebook, you'll want to set this to true so that you can actually reprocess the data for the first time. Okay, so just a little bit about what data we're actually using in this demo. So this is using commissioning data from JWST program 1448, observation 11, and it was focusing on background in the 1.2 min-body benchmark field. This is actually a publicly available data set, so there should be no need to provide a mass token when you're downloading this data. However, if you use this notebook to do similar processing on your data, this may be needed. I'll note that this was a data set that used 3 shutter slitlets. It was also using a 3-point nod dither pattern, but since we're just demonstrating how to do master background subtraction, those work individually on the exposures. So we're only going to pull down one of these rate files in addition to the MSA metadata file so that the pipeline can actually run what it needs to run. You'll also notice here that I'm downloading an updated bar shadow correction reference file from CRDS. This is a special case for this data set because the use after date on this reference file is set to slightly after this data set was taken. So I just wanted to process this data with a version that was derived from in-flight data. You may not need this. It would probably correctly pull down for any non-commissioning data sets. But this can also serve as an example if you need other kinds of reference files from CRDS and you are trying to figure out how to download and to override. Okay, so let's get started into this process a little bit. So the first thing I'm going to note here is that in order to achieve the best results with master background subtraction, we actually are going to recommend that you first check or vet your input background spectra before you do any kind of additional processing. And the reason is because should any contaminated backgrounds, like those affected by stray light or unmasked hot pixels, be utilized when you're generating the master background spectrum, it's going to impact the quality of that master background spectrum and also the resulting background subtracted spectra. And we'll see that in a few plots that I have in this notebook. But you'll notably see that hot pixels are going to be introduced as these positive spikes in the background spectrum, and those translate to then really negative spikes in your final background subtracted spectra. So we should really be handling those pixels and addressing them before you create the master background. Otherwise, you're going to get some really weird results. So this is just the directory we're going to save these results in. We're going to go ahead and just calibrate, extract, and analyze the background spectra alone. We're not going to do any type of background subtraction, so I'm making sure to skip over master background as well as the pixel-to-pixel background step, just to be sure. And these, I will note one thing, that I have also, you'll notice throughout the notebook, whenever I call this stage 2, I edit these slit Y low and slit Y high parameters. And these just kind of modify the WCS cutout of your slitlet. And I just found that these adjustments were better centering the slitlet in the cutout. You may not need to do this, but these are parameters that you can kind of mess with if you need to when you're processing different data sets. So again, this has been rerun, so it's going to say runtime 00, but let's just go ahead and jump right in and kind of look at what kind of background spectra we're working with in this data set. So I'm actually pulling down a function that we imported. I call it mean background variations, and I'm pulling it from I think it's called master background plotting tools, the .py file that's should be with this notebook as well. And this spectra is doing, this function is doing just a few things, and I'll note them here because we'll use it again later in the notebook. But essentially, it's doing some basic filtering where it's trying to identify any extremely contaminated backgrounds, and it'll do that based off like how it deviates from the median background. If anything is way deviated, it'll just go ahead and filter it out. I also have it set up to kind of identify those hot or bad pixels in the spectra, and trying to replace them with the median value in the stack to kind of create this. This in blue here is a sigma clipped mean background that I've calculated. And I've also, in this plot, have calculated the coefficient of variation between those background spectra and that calculated mean background, just to kind of get an idea of maybe how this background is varying over your field of view. This is particularly useful in this case because this entire data set was looking at backgrounds, so there was quite a lot to filter through. And this kind of just gives me an idea of what I'm working with initially. And in this case, the variation was within a few percent. So I just went ahead and from these good slits that were plotted above, I just pulled a handful out to use as demonstration for this notebook. And in addition to that, I kind of just plotted each of those individual ones that we're seeing here. And I'll note here that I specifically included one of these backgrounds to have an extremely positive spike in this, a hot pixel spike, just to kind of show you later on how this is going to impact the master background spectrum if you leave this in. And so these are just the other backgrounds that are going to go into creating the master background. I also included one with this sort of dip feature that shouldn't be there. Okay, so before we go ahead and see kind of what the pipeline default returns, I'm just making a note here that this particular data set, I needed to edit the metadata file. So this is information we already seen in the notebook from Dan, but I will make a specific note here in case you also need to modify your MSA metadata file to do master background subtraction. And the key thing that I'm also pulling this function that is editing this metadata file from that same .py file. You can find it there. But essentially, I'm defining which slits I want to treat as background. I also just randomly chose one to treat as a source. So we're not actually dealing with like a point source or anything like that in this case. I simply only have background in this data set. But the important thing that is needed is if it's a background shutter, you need to make sure that background is defined as yes in this column, and that source column here at the very end in this table, and it should be set to no. So those are the two important things to note here in order for the pipeline to do master background subtraction, because if you don't actually have anything defined as a background shutter in your MSA metadata file, master background subtraction will get skipped on the pipeline. Okay, so let's just go ahead and so here we're just creating an output directory for saving these files. For the default, we'll just make sure to have skip set to false. We also want to make sure that we're saving results so that we can like review what actually got returned. Similar steps here, similar parameters. Okay. So now let's go ahead and kind of take a look at the master background spectra that got returned when we did this with the default settings. Here is the 1D master background spectrum that actually gets returned, and right away we can already tell that since we didn't handle that one hot pixel that was in one of our input backgrounds, that it persisted in this, our creation of the 1D master background. And consequently, because it's in our 1D master background, it is in every single 2D master background that is for each of the open slits, and it comes across as this bright band. And so if you look at your final results, then after that, you'll notice that, so this is the slit that had the really hot pixel here, so it's still there. But if you look at the ones where it didn't have it, you'll notice that instead of where that bright band was, you had this extremely negative dip. And you can imagine that if you had more than one hot pixels that were contaminating your spectra, that this would look a lot weirder. And so it translates in all of those. And so one thing we want to do and think about is how can we actually go and handle these hot or bad pixel contaminants that can show up in the background spectra. And here I'm just going to show one way to manually update the DQ flags for those pixels. This is also calling another function from that .py file. And it actually works best if you install this Python package called Plotly, and it allows for interactive plotting. I found that was best to identify the locations of the problematic pixels. So here's just an example. Let me go to the better example. Here we go. Here's just an example of that slit with that really large hot pixel. I've already identified them here in this notebook, but for these demo slits at least. But you can kind of see I've identified them up above, and X's have been placed on the pixels that we flagged. And I'll just note that after you have identified the pixels you want to update the DQ flags for, you might want to make sure to rerun this cell with the update DQ flag set to true so that the DQ flag actually gets updated. Okay, but I will note that this can be an extremely tedious process, especially if you have a lot of background spectra. But it's still a useful way to go ahead and update the DQ flags for, in some cases, say you had like a hot pixel in your science spectrum and you need to handle it that way. This could be a quick way if you have less science than background. So you can kind of figure out if you need to use this kind of method to update your DQ flags. But in this case, I wanted to try and do something a little smarter so that I didn't have to go through all that. And so we're going to go ahead and supply our own 1D master background to this data set. And if you'll remember, I mentioned that currently in the pipeline, you cannot modify the extract 1D parameters when the pipeline is extracting the background spectra, at least when you're running it with the defaults. So since we're supplying our own, we can actually go ahead and modify the region, because by default, for extended sources, the pipeline will actually only extract the central 6 pixels of your slit. In this case, I have 3 shutter slitlets with background in all 3 shutters of the slitlet. So I want to go ahead and try to make that extraction region larger to cover more. So that's kind of what I'm doing here. I'm just modifying the extract1d reference file and rerunning it on the S2D files only. So we're not going to rerun the whole stage 2. We're just going to rerun the extract1d step on those resampled products. And so this is the same plot that we've seen before, except it's only plotting the demo slits. And there is an option with this function that I made that you can save this sigma clipped mean as an X1D file, because in order to supply the stage 2 pipeline with your own master background, it has to be in the format of an X1D file. So just keep that in mind. So this is the same similar setup, except the only thing different is we're going to actually supply a user background. And once we do that, we can actually see the results that get returned. We already see that the master background looks a lot better. We don't see that really hot pixel positive spike there, and we don't see it in the 2D spectra anymore. And if we look at the final results, we can see, there could be a little more cleaned up for some things, but essentially we can see that we're basically around 0 now that we've subtracted the background. We're not seeing these extremely negative dips. You might see some edge effects at the very edges, just because of how resampling does things. So you might see some spikes here at the edge, but you can clip them. And that is essentially it for this notebook. And if you were actually looking at, some actual source data and you had multiple exposures, you can now actually put that into the Spec3 pipeline and generate a final combined spectra.